Thanks very much. Good afternoon. Well, it's been tough to live up to these intros and the build-up. I'll try to do my best. You will see in my comments, it will look like Nick and I choreographed, engaged in a pas de deux, hopefully not a folie à deux, with the points that we're making. You'll see an echo of many of the things that he brought up in my talk. I also want to point out that I dressed for the occasion. This, I used to have a slide that would help you. This is a tie. I call it affectionately my FDA tie. And what it has on it is all these sort of pictures of these nostrums and elixirs and things that were sold around the turn of the century, which actually gave rise to the FDA, because these were based on claims for health benefits using the language of science. And of course, many of them not only were not very effective, but were downright dangerous. And this gave rise to a reaction among doctors, which ultimately created the modern FDA with its rules of science that you had to obey before you could make these claims. And now we're in another era, but I will argue not actually so different, but different in subtle ways, not in dramatic ways. Now, I call this Science on Trial, interestingly, because originally I was planning to feature, which some experience I had literally in trials around science, and particularly around vaccines and autism. I was going to show you some of the transcripts of that. I decided to back away from that. It was a lot of rather more complicated, but also my partner in that was a faculty member here some number of years ago named Eric Fombun. The way that language was used to counter the claims of safety was very, very interesting, and maybe those will come out in the comments. I have a lot to say about the interplay in the anti-vax movement, which is actually far more complex and nuanced than is sometimes portrayed. The anti-vaxxers are not, they will say, either anti-vaccine nor anti-science. And when one engages with them seriously, you find you're in a much more complex debate than it would seem. So I may get some of those comments in. So I just want to point out that society has never been completely pro-science. We've always been anti-science, anti-certain inconvenient forms of science. From Galileo with the promotion of heliocentrism, to evolution, to germ theory, genetics, pollution effects, vaccine safety, climate science. These are only the most recent manifestations of this, but society has always been resistant to certain claims of scientists that challenge alternative sources of power and authority, and I hear some of the commentators have real expertise in this area, so I'm not going to go too far. But if the scientific claims challenge the authority of religion or politics or money, this is when we push back. But it's important to segment things, because not all science is necessarily resisted. It's inconvenient science and science that challenges this authority. And sometimes this lens is widened and sometimes it's narrowed. But I would not necessarily call the current era necessarily more anti-science than it has been in the past. We've always been anti-certain forms of science, but what is very different today, I will say in the political sphere it's a little different, I'll talk about that. And things like this, which all of you have read just in the last few days, shows that you don't need science to not make ridiculous claims in public. And in this case, it's a situation with Trump repeating claims about the trade deficit that he actually knew to be false. So using science to show that it's false doesn't prevent you from completely rejecting and asserting things that, in fact, in this case, he knew was false. So this is going to be part of my point today, is that although science can provide language for people who are resisting science, they don't necessarily need that language. They can just dismiss it out of hand. So we have to be careful about saying what science is enabling or producing versus what science criticism is actually doing. So there is something different within science, though, and I say this is the new meta-research and science reformers movement. And I think these days the criticism that is normal within science is going beyond individual theories to either field or method-wide problems. And it also is extending to the core value indicators, that is, which we can also call incentive structures, that is publishing, funding, promotion. These are exactly the markers of successful science, and yet we're now seeing them or labeling them as perhaps a structure that distorts science. So this is very different. And also, many of the science reformers who are regarded as self-appointed, to some extent we are, and these come typically within science, and they're criticizing science or the manner in which science is done beyond the customary disciplinary debates. So again, science is full of argument. That's what science is. It's full of argument, but it's argument that takes a certain formal, structured form. That's the way it is. And that it's a form that we think gets us closer to truth. But the nature of these debates are widening, and the people who are engaging in debates are different, and they're challenging more fundamentally the scientific method, it would seem, than others. And also, they come from outside the disciplines, which is very threatening. It's also sometimes a little misguided, I will say. So it's an important balance. They bring a necessary perspective, but sometimes it isn't as informed by the texture of the discipline. So when we have this conversation, I think it's really critical to specify which actor or actions that we're concerned about. So this degree of specificity I hope we'll get in the discussion. Are we concerned about other scientists within or outside your discipline? Are we concerned about the effects of science criticism on policymakers, on funders, on industry, on lawyers, with the media, with the public? So each of these engagements, the concern is going to be different. So I hope we get to that level of granularity. And then I hope we also are specific about what are we worried about. That is, that the anti-scientists, which I'll put in quotes, often these anti-scientists are sometimes scientists themselves, will use the rhetoric and logic of science, of the science critiquers, to decrease trust in or reliance on good science for personal decisions or public policy, decrease public funding for the science they are castigating, confuse the public about issues affecting their health or political choices, harass scientists, recruit scientists to testify for their cause or win legal settlements. I want to say that all of these can be and are done without a scientific rationale. We don't necessarily need science to do any of these. Using this language of science reformers is often just window dressing, and I'll make this point. But we don't like it because we're particularly susceptible to it. But we shouldn't mistake it always as the cause. And I'll show a few examples. Now, I want to talk a little bit about an example of how open science itself can be used as a weapon. And I think this is the kind of thing that motivated this conference. How many people here know about the 6 cities study? Any hands? 1, 2, 3. Okay. So this is one of many, 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 many examples that should be part of everybody's toolbox. So, and you'll see why. So this was a study that was done in 6 cities. You can see them on the slide: Topeka, St. Louis, Portage, Steubenville, Kingston, and Watertown. That showed that particulate matter had an adverse effect on mortality. And this is the basis for EPA regulations, and this was published in the New England Journal of Medicine. This immediately provoked a reaction in industry, saying that they wanted to get access to the primary data. They didn't believe it. And they pushed back very, very hard, and there was a huge struggle over getting reanalysis of this data. And you can see here the Harvard researcher whose early work led the no-lead policy for gasoline and McCarthy and won a Genius Award. There's no point in providing information to industry thugs. Here's an article about it that appeared in the Wall Street Journal, and I'm going to ask, whose side are you on? It says, Dr. Schwartz pointed out that when industry critics reanalyzed the research supporting rules to ban lead in gasoline, which he was also involved in, that's not what this was about, scientists had to defend their work repeatedly, a distraction he views as harassment. No epidemiologist can afford to be buried in so much time-consuming controversy for every study. That's what the industry promises for every data set they get their hands on. On the other side, we have fellow David Murray, who says, I have a big problem if somebody's denying access to the data because it might undermine faith in the results. This is exactly the language that open science and transparency reformers are using today, as evident. Now, why this is particularly important is it has given rise to legislation. The first thing was the Shelby Amendment. How many people know what the Shelby Amendment? This is in the U.S. I apologize, I'm here, you use focus. So the Shelby Amendment was a little thing put into a budget bill that said that any regulation, the data behind any regulation that had any budgetary impact had to be made available to the public. Ooh. This was part of OMB. This, in turn, gave rise to this, the Secret Science Reform Act. This was in 2015, to prohibit the EPA from proposing, finalizing, or disseminating regulations or assessment based on science that's not transparent or reproducible. You know what this is about. So this didn't go through, even though it was approved by the House. So what do you get? Resuscitated, 2017. We have the Honest Act. The Honest Act is the same act with only a couple lines changed. Again, no regulations based on assessments that are not transparent or reproducible. I'm going to show you some other text here, and you can read up there. Honest stands for Honest and Open New EPA Science Treatment Act. This was passed. It's waiting now for Senate approval. And it says, no rule should go through that isn't covered by the best available science that's specifically identified and available online in a manner that's sufficient for independent analysis and reproduction. And this is the details, and this is actually the whole act. The term scientific and technical information includes materials, data, and protocols, computer codes and models, recorded, basically the data sets, and how to access and use that information. This is the reproducibility script. This is it. And it's being used against, in a sense, what we would regard as the best use of science by the government. And as I point out here, the principles and tools of legitimate science reform can be hijacked to weaken reliance on science. And this is a paper written by people who were involved in the six-city study. The six-city study ultimately was completely, at the cost of millions and millions and millions of dollars, completely reanalyzed, partly by these folks. And it took 5-6 years. They showed exactly the same effects. But what these folks did is they created a model, they put it all online, and they published this paper, which had a big influence on me on the criteria for reproducible epidemiologic research. Their table 1 is the criteria for reproducible research. Now, this is reproducible only in the sense of seeing exactly what went into creating the results. And here you see, this is the script for the Honest Act. The data, the methods, the documentation, and the distribution. This is it. This, in a sense, this table 1 became the pages of the Honest Act. And what ultimately that will mean is that APA will rely on much, much less science, because most of it actually literally cannot be made public. So, but do they need that? This just appeared 2 days ago. No. They can decide not to rely on science without saying it's bad, without saying it's not transparent. They can just dump it, which is exactly what they're doing. So the question I think that it would be interesting to discuss is how much is this critical language, how much of this hijacking is really going in, even if we got rid of all that, would it prevent some of the worst stuff from happening? I don't know. I actually don't think so. I think it pretties it up. It provides a veneer, but if people are going, this is raw politics. Now I want to talk about another thing that we have a problem with. I think that we're shooting ourselves in the foot, which is the talk about reproducibility. And I will argue that it's an inappropriate metaphor for reproducibility, and I'll make that clear as we go along. So here's a meta-analysis published in 1988, very famous one by Richard Peto, on the effect of tamoxifen in the treatment of early breast cancer patients. So what do we see here? And I'll have to orient you a little bit. Let's see. I can't work this cursor. Oh, there we go. So here is the line of no effect. Here are studies who have various point estimates, that is, estimates of relative risk, and everything to this side is on the side of protection, that is life-saving. And the bars are the confidence intervals. And you'll see that almost every bar, in fact, 22 out of 23 include the null effect. That is, these are 22 studies that had non-significant findings. Only one had a significant finding, but it adds up, and this is the dotted line, to a highly significant 20% mortality reduction. So if we were in the reproducibility business, we would say that we have reproduced a finding of no effect 22 times. And yet, when you view it through the proper epidemiologic statistical lens, in fact, the evidence has added up to show the highly compelling 20% survival benefit. This slide needs to be burned into the brains of those who talk about reproducing results, and we'll go in a little bit more into that. So it also motivated us to write a paper on what does research reproducibility mean, and our argument is basically this. There are lots of words to describe reproducibility. Reproducibility, replicability, repeatability, reliability, robustness. I don't know why they all start with R. There's actually one more that I've forgotten. Generalizability, then we get the rhetoric of open science and transparency. But what we're really talking about is truth. That's what we're really talking about. We're not talking about reproducibility. That, to the extent it is at best a means to an end. But sometimes it comes back and bites us, and I'll explain how that's happened. So we outline these three aspects of reproducibility. One is methods reproducibility. So in many sense, this is how the word is used, and which is simply, are you transparent enough about the data, about the methods, so somebody else could take the same data and methods and see how you got your results. So that's one use of the word reproducibility. The other is what we call results reproducibility, sometimes called replication, but sometimes replication is used for the first one, so it's very confusing. But results is you do another study, quote unquote, like the first study, and you get, quote, the same answer. The third is inferential reproducibility, which I think is undervalued and often ignored, which is that you have the same results, but you get similar conclusions. And the reason I really emphasize this is p-values and data do not speak for themselves. A p-value cannot be false, and this is where I maybe differ from my colleague at Stanford. A number cannot be false. A claim based on that number is false. A scientist makes the claim. So if you get a significant result for something that's very surprising, you don't have to claim that that is real. In fact, you might say that it's spurious. You should, if you know how to do proper inference, say that it is spurious. The claim is wrong, not the result. The result might lead you in the wrong direction, but that's a complicated thing I'm not going to get into. Here's just a few weeks ago now from the New York Times, which used the word inference in the title. I liked it, and makes a similar point. So the problem is that the reproducibility framing, I'll show a better example, a yet better example in a minute, it feeds the science is broken narrative. The idea that we do studies and then they're refuted. We have issues with that, there's no question. But for the most part, most studies are actually consistent with each other when you consider the full range of uncertainty. So our intuition about reproducibility is fundamentally flawed because it comes from sciences where the signal is very, very high in relation to the noise. So if you find in physics or, if you can't reproduce, if you have two things crashing into each other and then they crash into each other again, something fundamentally different happens, that's a problem. But in biomedicine and in many empirical sciences and social sciences, the signal is barely higher than the noise. It's just the nose is right over. In fact, we power them. 80% power is, with a 5% type 1 error, you're engineering it so the signal is barely higher than the noise. So you cannot talk about a significant and non-significant study as even remotely be in conflict. So most complex science is not a series of proofs and disproofs. We develop complex networks of evidence that strengthen or weaken the evidence. And we sometimes call that consilience. So the real question is, what's the strength of the cumulative evidence? And how efficient is the scientific enterprise in getting to the truth? can we get there faster? And this efficiency narrative includes the percent of research that's uninformative, which to me is much realer in my experience than the amount of research that's just plain wrong. It's just that it tells you nothing, or nothing of value, because the questions are misaligned with the methods, the questions are uninformative. This is what I worry about when I look through the literature, and I'm sure all of you have the experience. You just paid page after page after page of research that really doesn't tell you very much. So including uninformative science in the sloppily done or messily done science is an important contribution. So I want to show this. You showed that this is a very important and highly visible paper estimating the reproducibility of psychological science. And on the left, you see the distribution of p-values for the original studies, and the dotted line is, of course, 0.05. And on the right is the replication. So that looks like, boom, you know, nothing held up, real mess. You know, the p-values go from 0 to 1. And on the right is, as far as I was concerned when I saw this, the only story was just found on the left-hand side. That is, every study they looked at from the top psychological journals was significant. So obviously they were being selected for significance. That's the only story. So if studies are being selected for significance, if you do the studies again, you'll get a regression to the mean. Okay, so is that plausible? So I just want to point out, in this study that was about reproducibility, they didn't have a definition for reproducibility. They couldn't define it. That's a problem. They defined it as a difference in significant levels, whether 50%, and the reason they had 5 is because they couldn't, it has no real good definition. Whether 50% of replication effect sizes exceeded the original, whether the effect size within the confidence interval of the original, whether the combined estimate was statistically significant, and finally, this is when you give up, subjective impression. So the whole project, I mean, this was an expensive, big project. They didn't have a definition of their primary endpoint. That's a problem. So here's the same data. So just on Friday, I just ran a little simulation, 1,000 trials, where in 2 columns, 1,000 trials on the left, 1,000 trials on the right, random, and I assumed that the effect size was just half, was just 1 standard error. Okay? So, and then I published, I only selected the rows where the p-value on the left, where the p-value is less than 0.05, and I have the distribution of the other column among those rows, and this is what I got. This is literally what I got. Those are the quintiles. The lines up top are the quintiles of their distribution, with the median around 0.25. I got exactly the same. Exactly the same. Just from, and so what does this tell us? The pattern was created by publication bias, which you learned only from looking at the first sample without even engaging in the exercise, and then regression to the mean. If you selectively choose studies that were random highs, the second study, and all of the studies, every single one is compatible with the other. They were all generated from the same, from the same mean. They're all compatible, none of them. Let's look at the text of the New York Times article that covered this. What you'll see is many intertwined narratives. Even they are confused. Paragraph 2. This is on page 1, by the way, of the New York Times, 2015. Their conclusions have confirmed the worst fears of scientists. Paragraph 5, more than 60 of the studies out of 100 did not hold up. Paragraph 9, the new analysis found no evidence that any original study was definitively false. Rather, it concluded that the evidence for most published findings was not nearly as strong as originally claimed. That's maybe fair, particularly if you choose the original finding. It's not the original finding, the ones that were selected to be in these journals because they were significant. The journals arguably are at fault, not the scientists. Paragraph 11, this report appears, so this follows immediately, at a time when the number of retractions of published papers is rising sharply. So retractions are like really usually messed up science. It's not this. So this is intertwined with a retraction fraud and misconduct narrative. And finally, paragraph, you have to really stick with this article to get to this paragraph. Yet very few of the redone studies contradicted the original ones. Their results were simply weaker. Quote, we think of these findings as 2 data points, not in terms of true or false. Well, wait a minute. Worst fears of scientists? 2 data points? didn't hold up. So you can see there's a lot of confusion here by adopting this narrative. So this actually was picked up by Catherine Hall Jameson, who's a very renowned commentator on science communication, and she pointed out, interestingly, that in 2016 to 2000, this is a very comprehensive paper. I'll just point out this, that the top 10 science articles were all about scientific achievements. None of this narrative on science is broken was part of the top 10, except an article on medical errors. So the extent to which this is dominating scientific conversations is unclear. I mean, scientists, we have to remember, is still creating wonderful progress. And again, the issue is, can we get there more quickly and more efficiently? And this actually has been taken up. There was a series in The Lancet. Philippe, were you part of this? Yes. So he was a whole series of papers on how basically there's a lot of research waste, and you can look at all the different phases of research conduct and reporting as sources of waste. They had this flow chart, the research waste. It's really research efficiency. It's like, when do we not make the best use and how? This is a survey in Nature about science that's not cited. A pretty sizable percentage, unfortunately. Some years from publication in many sciences is different by science. 4 years from publication, between 10 and 40% of studies are completely uncited. That to me is very inefficient research. If it's not leading to anything, if the citation indicates it. This is 0, not 1, not 2. That arguably isn't so much either. This is 0. So what do we learn from those, and how can we get rid of them? This is from the NIH. A lot of clinical trials were not being published timely way, particularly those based on surrogate endpoints. That's certainly research waste, right? We're not even learning. Clinicaltrials.gov will hopefully go some way to getting rid of that. So to finish up, and there are many things I left on the cutting room floor, so hopefully if people are interested, that will come up in the later conversation. Shifting from a reproducibility paradigm to frames of research efficiency, cumulative evidence, and truth brings many benefits. Uninformative research comes into consideration. You don't have to define reproducibility. It just becomes either strengthening or conflicting, reinforcing or non-reinforcing evidence. It allows us to improve science without being anti-science and declaring that science is broken. Everybody's in favor of getting to the truth faster. And to go back to the first part of the talk, I think we have to be very, very careful about framing about what are we worried about and what are the effects of science criticism. It doesn't, even when the language is invoked, it doesn't necessarily mean that that is the source of the way science is being contested, and if we didn't give them that language, they'd probably find another way to do it as well. So I need to stop here because this study says that not only have I bored you, but this talk has been completely ineffective. But fortunately, I read a lot, and the next study said that that study was wrong, so maybe we've achieved something. So thank you very much.
Thank you very much, Steve. Next up, we have Richard Harris.